Hello everyone. Today we are going to talk about one of the most fascinating moons in the solar system, Enceladus, the small icy moon of Saturn that hides a global ocean of liquid water beneath its frozen surface. And the news is exciting. Researchers analyzing data from the Cassini mission, which ended in 2017 but continues to surprise us, have discovered complex organic chemistry within that alien ocean. These molecules are the building blocks that, on Earth, lead to life. Could Enceladus possibly harbor living organisms? Let's explore this extraordinary discovery. Before we dive into the recent discoveries, we need to set the stage for the mission that made all of this possible. The Cassini spacecraft was one of the most ambitious and successful missions in the history of space exploration, an epic collaboration between NASA, the European Space Agency, and the Italian Space Agency. Launched in 1997, Cassini took 7 years to reach the Saturn system, arriving in 2004. Over the following 13 years in orbit around Saturn, the spacecraft completely transformed our understanding of the ringed planet and its complex family of moons. It made groundbreaking discoveries about Saturn's atmosphere, revealed intricate details of the rings, studied the icy moons, and even deployed the Huygens probe, which landed on the surface of Titan. But perhaps Cassini's most important discovery, and certainly the most relevant to the search for extraterrestrial life, came in 2005, when the spacecraft detected plumes of water vapor and ice particles being ejected from the surface of the small moon Enceladus. This spectacular observation proved beyond any doubt that Enceladus harbors a global ocean of liquid water beneath its icy crust. The Cassini mission ended in September 2017, when the spacecraft was deliberately plunged into Saturn's atmosphere. A final maneuver known as the Grand Finale, designed to prevent any possible contamination of potentially habitable moons. But while the spacecraft itself was destroyed, its scientific legacy endures. Cassini transmitted terabytes of data during its operations, and scientists are still analyzing that treasure trove of information, making new discoveries years after the mission's end. Enceladus is a small moon. With a diameter of only about 500 kilometers, it could easily fit within the borders of Texas. But what it lacks in size, it more than makes up for in scientific intrigue. Its surface is covered with bright water ice, making it one of the most reflective objects in the entire solar system. The most remarkable feature of Enceladus lies at its south pole. There, parallel fractures in the icy crust, poetically nicknamed the tiger stripes, are the sources of the spectacular plumes Cassini discovered. These cryovolcanic geysers eject water vapor and ice particles at speeds of hundreds of meters per second, forming plumes that extend hundreds of kilometers above the surface. But where does this water come from? From a global ocean of liquid water that lies beneath Enceladus's frozen crust, at an estimated depth of several tens of kilometers. This ocean remains liquid despite the frigid temperatures of the outer Saturnian system thanks to tidal heating, the same mechanism that keeps Jupiter ES Moon Io volcanically active. As Enceladus orbits Saturn in a slightly elliptical path, the giant planet's immense tidal forces flex and deform the moon. This flexing generates frictional heat within Enceladus's interior, enough to keep its ocean liquid and drive the dramatic geological activity that powers the south polar geysers. Here's where the story becomes even more fascinating. The material ejected from Enceladus's geysers doesn't simply fall back onto the surface. Some of it escapes the moon's weak gravity entirely and goes into orbit around Saturn. Over time, this material forms one of Saturn's faintest and most diffuse rings, the E-ring. The E-ring is the largest and outermost of Saturn's rings, stretching hundreds of thousands of kilometers across. It's composed almost entirely of tiny particles of water ice, quite literally frozen material from Enceladus' subsurface ocean scattered around Saturn. This connection between Enceladus and the E-ring was conclusively established by Cassini and represents a truly unique system in our solar system, an alien ocean continuously replenishing a planetary ring. For scientists interested in studying the composition of Enceladus's ocean, this setup offers an extraordinary opportunity. There is no need to drill through kilometers of solid ice to reach the ocean. Enceladus is conveniently venting it directly into space, where spacecraft can fly through the plumes and collect samples. A Cassini estava excepcionalmente bem equipada para aproveitar esta oportunidade. Entre seus 12 instrumentos científicos estava o Cosmic Dust Analyzer, CDA. Este instrumento foi projetado para detectar e analisar partículas microscópicas de poeira no ambiente espacial ao redor de Saturno. O CDA funcionava como um espectrômetro de massa de impacto. Quando uma partícula de poeira atingia o detector a velocidades orbitais típicas, o impacto vaporizava instantaneamente tanto a partícula quanto uma pequena porção do detector. A nuvem de material vaporizado era então ionizada e analisada, revelando a composição química da partícula original. Este instrumento provou ser crucial para estudar Encélado. Em múltiplas passagens próximas da Lua, a Cassini voou diretamente através das plumas do Polo Sul, permitindo ao CDA analisar milhares de partículas de gelo recém-ejetadas do oceano subsuperficial. Estas não eram partículas antigas e processadas do anel E, mas amostras frescas do próprio oceano. A distinção é importante. Partículas no anel E ficam expostas por longos períodos à intensa radiação do ambiente espacial saturniano. Esta radiação pode alterar ou destruir moléculas orgânicas complexas, tornando difícil determinar o que originalmente estava presente no oceano. Mas partículas recém-ejetadas retêm sua química original, fornecendo uma janela não adulterada para a composição do oceano de Encélado. Em 2008, during one of its many close flybys of Enceladus, Cassini performed a particularly daring maneuver. The spacecraft dove through the plumes at an altitude of just 50 kilometers above the surface, much closer than on many previous passes. At this intimate distance, the Cosmic Dust Analyzer, CDA, was immersed in the densest part of the plumes, collecting a treasure trove of data from freshly ejected ocean particles. However, working with CDA data presents a major challenge. Interpreting mass spectra is far from straightforward. Complex organic molecules tend to fragment upon high-velocity impact, producing intricate patterns of spectral peaks. Identifying the original molecules from these fragments requires advanced modeling and often years of painstaking analysis. That is why only now, more than 15 years after the original observations and 7 years after the end of the mission, are scientists publishing comprehensive analyses of these data. Modern planetary science often operates on this kind of timescale. We collect data during narrow mission windows spanning years or decades, but then spend additional decades fully unlocking the information contained within them. A recently published paper in the prestigious Nature Astronomy journal reveals the results of years of meticulous analysis of Cassini S 2008 CDA data, and the findings are nothing short of remarkable. Enceladus AS Ocean contains a surprising diversity of complex organic molecules. First, researchers confirmed the presence of organic compounds that had been previously detected in particles from Saturn SE ring. This confirmation is crucial because it definitively establishes that these molecules originate from Enceladus's subsurface ocean, not from some external process occurring within the ring itself. Even more exciting, however, are the entirely new molecules identified for the first time. The list reads like a catalogue of advanced organic chemistry. Esters, aliphatic alkenes, heterocyclic compounds, and molecules containing nitrogen and oxygen in various configurations. For those unfamiliar with organic chemistry, these names may sound like technical jargon, but each category represents an important class of molecules with distinctive chemical properties. Esters form through reactions between alcohols and acids, and are common in biological fats and natural fragrances. Alkenes contain carbon-carbon double bonds, allowing for complex molecular chains. Heterocyclic compounds are ring structures that mix carbon with elements such as nitrogen or oxygen, the very kind of molecular frameworks found in DNA bases and many essential biological molecules. Why are these specific molecules so significant? On Earth, these classes of organic compounds participate in cascades of chemical reactions that ultimately lead to even more complex and functional molecules, including amino acids, nucleotide bases, sugars, and lipids. These, in turn, are the fundamental building blocks of life as we know it. It is crucial to emphasize, and the researchers are very careful to do so, that there's a vast difference between detecting organic molecules and detecting actual life. Complex organic chemistry does not imply biology. Many purely geochemical processes can produce organic compounds. We've found organic molecules in meteorites, comets, the atmospheres of giant planets, and even in interstellar clouds, none of which are known to host life. What these discoveries do establish conclusively, however, is that Enceladus's ocean is chemically rich and complex. It contains not only liquid water, which is essential, but also the chemical ingredients that could potentially support biochemistry. In that sense, the ocean is habitable, meaning it possesses the basic chemical prerequisites for hypothetical life forms. Combined with previous knowledge that the ocean contains dissolved salts, has an energy source through tidal heating, and shows evidence of hydrothermal activity at its seafloor, Enceladus emerges as one of the most promising locations in the entire solar system to search for extraterrestrial life. In the outer solar system, two ocean worlds stand out as prime targets in the search for life: Enceladus around Saturn and Europa around Jupiter. Both host global oceans of liquid water beneath icy crusts. Both show evidence of geological activity. Both are considered potentially habitable. Europa is larger, roughly the size of Earth's moon, with an ocean that may be deeper and potentially contains twice as much water as all of Earth's oceans combined. Telescopic observations and data from the Galileo spacecraft have hinted at occasional plumes of vapor erupting from Europa, though these are far less prominent and consistent than the geysers of Enceladus. NASA's Europa Clipper mission, currently en route to the Jovian system, will study Europa in unprecedented detail starting in 2030. It will determine definitively whether plumes exist, characterize the thickness of the icy crust, map the surface geology, and investigate ocean composition through remote sensing. But Enceladus has a crucial advantage. Its spectacular geysers provide direct access to the ocean. There's no need to infer ocean composition from afar. Spacecraft can fly directly through the plumes and collect actual samples. This extraordinary accessibility makes Enceladus an exceptionally compelling scientific target. With the recent discoveries of complex organic chemistry, Enceladus may be taking the lead in the race to identify the first extraterrestrial life in our solar system. The question now becomes, when will we return to Enceladus? The Cassini mission gave us tantalizing glimpses, but it was not specifically designed to search for life. Its instruments, while capable, had limitations. A dedicated life detection payload could achieve far more. Multiple mission proposals are in various stages of development. NASA has considered concepts like the Enceladus Life Finder, a spacecraft specifically designed to fly through the plumes with instruments optimized for detecting biomarkers. The European Space Agency has been exploring similar concepts. One of the most ambitious ideas is called Orbilander, a mission that would combine an orbiter with a lander. The orbiter would study Enceladus from orbit, characterizing its ocean and geological activity, while the lander would touch down near the geysers, analyzing freshly deposited material and potentially drilling a few meters into the ice to access deeper layers. Landing on Enceladus presents unique technical challenges. The surface is extremely cold, gravity is weak, and the Saturnian radiation environment is harsh. Yet engineers are confident that these obstacles are surmountable with current technology, making a return to this extraordinary ocean world increasingly feasible. The discovery of complex organic chemistry in Enceladus, ocean, marks a milestone in the search for life beyond Earth. While it is not evidence of life itself, it demonstrates that this small, icy world possesses the chemical ingredients and physical conditions necessary to potentially support biology. Enceladus conveniently offers us access to its oceanic secrets through its spectacular geysers. All we need is to return with instruments specifically designed to detect signs of life. The next mission to Enceladus, whether it is Orbilander or another concept, has the potential to answer one of humanity's deepest questions. Are we alone in the universe? Even if life is not found on Enceladus, studying this fascinating ocean world will immensely expand our understanding of planetary chemistry, habitability, and the limits of life. Each new discovery brings us closer to answering fundamental questions about our place in the cosmos.